Hello everyone, I'm Boris Lange, Manager Imaging Europe here at Edmund Optics, and in this video I'm going to talk about imaging optics and how they act and react in harsh environments. Give me just 1 second over here to make sure that everything is running nicely with the recording, but it seems to be all online and okay. So, without any further ado, let's jump right into it. We'll talk about shock and vibration, temperature changes, and at the very end also there's one slide about humidity. Stray light I just added for good measure because that's also something that comes up more and more as optics are taken outside of the factory, outside of the buildings. As soon as you're in the outside world and the sun might or might not be in your field of view, there can also be issues with stray light, but that's an entire discipline in its own and would certainly be beyond the 15 to 20 minute video that this is going to be. So, without any further ado, let's just jump into it and talk about shocks and vibration. And yeah, it's not surprising, we will have to need a closer look at the optomechanical design of a lens if you want to understand what's going on with respect to vibrations and mechanical shock. So this is a picture that I just got from the internet, quite a beautiful lens design, and the things to look out for in the context of mechanical shocks and vibration are things like iris leaves. It's usually the first things that break in a harsh environment, but also the focus mechanism is critical or can be critical, especially if you have a floating element design where it's a little bit of a more advanced mechanical design where the distances between individual optics or optics packages is changing when you focus the lens to different working distances, which is a great feature. It helps you to boost MTF performance. But in terms of a harsh environment and vibration and shock, this is a very critical thing because robustness is just reduced in such a focus mechanism. So the other thing to consider is of course the lens mount. Is it an F mount, which is already moving if you touch it a little bit because it's just a bayonet? Or is it a C mount, CS mount, M42 mount kind of lens mount that is, bottoming out and which, consequently is quite robust. Can also be an M12 mount, in which case the lens also can move a little bit within that threading and you also need to worry about how to lock it. And yeah, speaking of locking mechanism, there's of course also the locking mechanisms for the iris and the focus. How is that done? Is it also just a screw? A thumb screw, maybe you can replace it with a set screw, maybe you need to put a drop of glue onto that if you are really putting your optic on a robot or anything else that is moving rapidly or that sees significant accelerations on a regular basis. And then there's of course all the detail in the mechanical design. Are there any spring detents or there might be a lot of things in your optomechanical design that can break. That's the easy bottom line here. And the next step from there is actually quite obvious. Then you just remove everything that could possibly break. And a very easy thing to start with is really just the iris. You just replace it with a fixed aperture. So it's a piece of metal with a hole, essentially. So that's quite robust if you compare that to a fragile iris with all those different leaves that are carefully assembled together and grab into each other and that open and close very beautifully if you play around with that iris. But yeah, it's very clear to see how this is not very stable in a harsh environment, and so that's an easy fix as long as you don't need the flexibility on setting that aperture. So the second thing is the focus mechanism, and here I just assume that it's not a floating element design. It is a simple design that really just moves the entire optical package towards and from the sensor as you focus on different working distances. And if that's the case, then you can really get one step away and remove that helicoil focus movement and essentially simplify that whole thing by putting an outer thread on that lens barrel and then just screw it in and out like you would do with an M12 lens. The picture on the right here is a picture of one of our CI series. The I stands for industrial ruggedization, how we coin it. And yeah, it's essentially an M22 lens, if you want to call it like that. And the ring here on the rear side towards the camera is really just a C-mount to M22 adapter, and you can fix that screw once you've focused it again with 3 different set screws. So that's how a more robust solution would look like in terms of an optomechanical design of a lens. And yeah, at the same time, it comes along with more benefits. It's, as I said, more robust, but also it's more compact. You can save a tremendous amount of space here. You can also save a lot of weight, which also is quite critical in such an environment. And the nice thing, you also save some money on there, because you don't have the iris, you don't have the complicated focus mechanism. So that's really a good solution overall, with the only drawback, potential drawback at least, of a fixed f number. But as long as you maybe can identify what f number you need up front with a normal lens, with a C-series lens here, and then you know, yeah, okay, my exposure time with the camera, my LEDs, they all add up to, let's say, an f number of f/4. Then you can switch to the CI series lens, and then you will get the benefits of that are listed here, and you don't need to worry about any other f number, because you already identified that f/4 is going to be the name of the game for that particular application you're trying to solve. So that's it on the industrial ruggedization. But for more challenging systems, if I'm thinking about 3D cameras that have two camera systems that are carefully calibrated with respect to each other, or if you're really going to a harsh environment, robots that move very, very fast, this step might not be enough. You need more robustness. And so let's have another look at what you can do. So in a CI lens, the optics are still in retainers. It might be only one retainer for the entire optics train. It might be several retainers because the lenses have individual seats. Either way, that can be improved by just glue your optics in place. And the second idea is, and I already touched on that briefly, the focus mechanism, or the focus lock, I should say more precisely. We saw, here's that picture of that one set screw, and there's two more to that lens, but that's also not quite promising in terms of robustness if you have really a highly sensitive instrument or some very harsh vibrations going on in your system. So this can also be replaced with just a stainless steel focus clamp, as we can see it over here in our CR series. The R stands for ruggedization now, really, so this is as good as you can get. Because yeah, the advantage is quite clear. The entire torque is now nice. The entire force is grabbing the entire lens all around its diameter. No, diameter is the wrong word. Circumference is probably the right word in English. You know what I mean. You can see it in the picture. The entire lens is just grabbed by that stainless steel focus clamp. You fix it here with an Allen key with that screw, and then that's it. This lens is not going to move anymore. So this measures really eliminate the pixel shift and really allow you for a robust beam pointing. So that's exactly what you need if you have a 3D stereo camera in mind, or any other thing that is carefully calibrated. So drawbacks, yeah, they are a little bit bigger. They are heavier, stainless steel. And they're also a little bit more expensive, again, stainless steel. And also you need some more holes in there so you can glue the individual optics or optics packages in there. So that's also a little bit more of touch time on these lenses when you produce them. But that's really it. We can also have a more quantitative look at this and have a look at some beam pointing measurements that we have done for our CR series, and we put that next to our C-series lenses. So this is the standard lens, C-series lens, as you know it already off the shelf maybe. And yeah, you can argue that this is an outlier over here. But yeah, in this diagram that shows you how much the beam pointing is different from a lens before and after applying 50G shocks to it, you jump around in this field over here, which is maybe between plus and minus 5 microns. So that's the standard lens. And if you now go to the ruggedized lens, where we do all these things, right? We remove the iris, we glue the optics, we have the more robust focus lock. Yeah, we got to zoom in a little bit, and then you will see you're actually right around. We are below plus minus, the 1 micrometer pixel shift. And that's really something that you need. You might say 1 micrometer is really way smaller than any given pixel. Well, sorry, not smaller than any given pixel, but it's smaller than most pixels that are currently used out there. And but unfortunately that doesn't mean that you did a good job, because due to all the nice sub-pixel interpolation algorithms that are out there, that's actually a very common specification to achieve something that's better than a single pixel with your beam pointing. But it is what it is, and it works quite nicely. These lenses have already survived in very harsh environments. So that's essentially what I had to say today about the shocks and vibrations. That's the thought process behind that, at least for us, from an optical manufacturer, optics manufacturer. So, second part is going to be temperature. So let's switch gears and let's have a very top level look at this, and let's just take a minute to realize that not all lenses that are out there on the market actually have a temperature spec to begin with. And some might have only a storage temperature range, and some lenses also, I guess the least lenses maybe have an operating temperature range. And just to be clear, if you see something like an operating temperature range, say -10 to +50 degrees or whatever it is, that doesn't mean that your image is going to stay in focus over this entire range if you change temperatures. That rather means that at any given constant temperature within that window, the lens is not going to be damaged. It doesn't mean that you don't have to deal with the defocus. And so in that regard, that makes the entire topic of temperatures and how lens performance varies with it a little bit more complicated. Because it's a lot of work to come up with either the analysis up front, or also it's a lot of work to do all the measurements and really see how MTF reacts when you change temperatures. It's not widespread, or at least it's also very young technology. We'll touch on that in a couple of minutes. Let's just move on to the next slide and shed a little bit of light on why this is so complicated. And in the first step, let's discuss what is actually changing with temperature. If you look at just the optical design, just the glass elements, then yeah, actually each and every glass element is going to change. They're going to expand or shrink a little bit with temperature. So that the ratio between their thickness and their radius of curvature is changing, and that really essentially means that each lens element will change its focal length a little bit, and also the entire optical package is going to change its focal length if you mess around with the temperature. And to make things worse, also the index of refraction and Graben number consequently is changing with temperature. So that's like the raw material property, the index of refraction. And so that also might add up, or you should expect things to add up, not to zero. And all of these things will have a noticeable effect in your image. On top of that, there's the mechanical design. So also the lens distances with respect to each other is going to change as spaces also grow in size or shrink. And even worse, if the seeds are expanding a lot, then your optics might also become a little bit more loose. So now all of a sudden you have some tilt or decenters in your optical system. Or in the other way around, the metal is shrinking and it applies so much pressure on any given optic in there that the optic in the extreme cases is actually just breaking because it cannot withstand the implied mechanical stress. So summing it all up in one sentence, everything is actually changing with temperature, and you got to deal with it. Or at least you can deal with it, because there are things that we call athermal designs or athermal optics. And this is now just adding another level of complexity to the optical design process, right? So of course you can choose different materials, look into each and in every individual CTE, coefficient of thermal expansion. And then again, it's the art of optical design to add and mix materials in a way that overall these things add up to zero, and you will minimize the impact on MTF there. You can't really eliminate it, but you can take care and minimize it as good as you can by taking the according measures. Select different materials on the metal, see how you can carefully think and consider how you seat the optical elements. Maybe you also cannot use certain glass materials, even if you would like, because you need something else in there that has a CTE that compensates the rest of the system. So that's all the fun that's involved when you do this during the design time. So quite obviously this implies that the design is now taking a longer time. You're restricting yourself in terms of the material you can use. This again might in the second step also drive cost. And of course everything will also let me put it the other way around. you should also at the very beginning of such a project talk about the metrology behind this, because it's not self-explanatory that everything you could possibly think of or require in your application is already, that there's already metrology equipment for that around and at your optics manufacturer of choice. So it might very well be that you need to develop custom metrology to make sure that the performance of the imaging optics meet your needs here. That's another thing that adds time and cost to the project, of course. So it needs to be discussed right away in order to avoid any negative surprises here. Okay, so the last remark on that is that if you take all this time and worried about the optics and you did an analysis and all the measurements that you could think of, then at the end of the day, you still care about the system level performance, right? So this is really just to say that an athermal design by itself doesn't really do the job already. There's a lot more to it. When we do our custom imaging lens designs and someone needs an athermal performance, then that implies a lot of work also from you as the customer there in that situation. We need to understand how the interface between the optic and the camera looks like. How does it react? Where does the sensor move with respect to the optics or to the mount? How is the optic mounted in general is a question. What material is the lens mount made of, right? There's lots of details and lots of questions that need to be resolved. And if you want to do a custom project like this, you should expect a weekly meeting with us, at least for 2 or 3 months, until all of these details are figured out. Just rough numbers here, to give you an idea. Another thing to keep in mind is in your application, how fast is the temperature actually changing? And also, is there directionality? So is all the heat coming from one side, or is it all around the imaging system? So there's lots of questions. And at the very end, you're not stuck with try and error. You can find a sweet spot between let's do analysis up front to a certain degree, and then let's do some testing of the optics only to a certain degree, and then let's move on to the next phase of your project. And then you can have the prototypes and test the entire system and see if everything reacts as planned. But this is at least an option for custom imaging optics that we develop. And for standard parts, I think by now you have a good impression that this is a lot of work, and nobody, or not nobody, but most people, I think at least, do not do this if they develop products that just go on the shelf. For such a thing, it might just be worth it to just buy 1 or 10 and test them directly on your system and see how these optics react. And if there's problems, you can also, of course, at least contact us, and then we have a discussion about what can be done in order to desensitize, how do you say that in English? To make the design less sensitive with respect to temperature changes. Good. So at this point, I would already like to make some conclusions. The first one is, over the last, let's say, couple of years, there is really the trend that many applications out there require good imaging optics, right, that withstand temperature changes. Yeah, it's not only if one temperature stays constant, it delivers what it's supposed to be. It's really now the lens is in the factory, now it's outside. Now temperature is changing by 10 degrees, but of course I still need a good level of imaging performance. Lots of applications drive things like that in agriculture space, in the autonomous space, but also the high-end factory automation and metrology side of things, especially including robotics, really have a big demand here. And we're certainly happy to hear that call here at Edmunds. So we've always had, of course, the expertise, but quite earlier this year, we made the decision before, I guess, but earlier this year, we opened a new design center in Tucson, Arizona. We already had an office there with designers, but this new facility is now really focusing on optical design, on the metrology. Also, the project managers are sitting there, and even the prototype productions in there, all in one house. And there's a lot of things in there, I mean, people and also metrology equipment that address these market needs that we discussed today. And also here in Europe, I'm happy to report that we're strengthening our team. So in August, we'll have 2 optical designers also sitting here in our Mainz office in Germany. So that's also going to be very nice and promising. That'll greatly increase the speed of the turnaround time of our custom imaging projects. So that's fun and something to look forward to. I didn't forget about it. There's one more I wanted to touch. Humidity. I think we are already, quite late, I guess. I think this was supposed to be 20 minutes and this is what we just hit. So humidity is quite fast. I'll wrap it up. Either it's not a problem because you can use protection tubes that go on your camera and then you don't need to worry about the optics at all. But if that's not possible, for example, because you're using a short focal length with a very wide range, then you can also use waterproof lenses that are out there on the market. For example, our own CW series, which by the way are nominated for the Inspect Award. So I'd appreciate it if you take the time and have a quick look at those. They've got some interesting USPs that we believe bring some value to the market. And if you like what you see there, I would of course be even happier if you click on that product line and give us your vote in the upcoming Inspect Award. So, speaking about advertising, I already recorded another video for the UKIVA conference here where I explained some things within the context of taking a lens beyond the spec sheet. And if you also looked at that and if you found that interesting, or if you think optics is an interesting thing in general, please allow me to highlight that there's an upcoming webinar from Photonics Hub. So just Google Photonics Hub in my name or Photonics Hub and click on events. And then it's the 4th entry in that list. It's not for free, it's 70 euros or around about 60 GBP. But it's still a fun thing to do if you want to spend 2-3 hours listening to me, I guess, talking about optics. But enough about this whole advertising thing. Or maybe one more, there's going to be a panel discussion as well within the UKIVA conference here that I'm proud to be a part of. So look out for that. I think this is also going to be a fun session. There's lots of high profile people on that. I'm not talking about myself. I'm more referring to the other guys on that panel. With that, I think that's all that I had for today. Thank you very much for listening in and your attention, and I see you around.